Really appreciate those of you who can stay before going to get some food. I know I'm between you and food. Today I'm going to talk about making connections count with SCiP, or Silicon Photonics Chiplets in Package. My name is Rebecca Schaevitz. I am in the Optical Systems Division at Broadcom. I'm both a product line manager as well as a principal engineer, where I focus on the optical connectivity, specifically how do you get light on and off the Silicon Photonics chip. Before I get into the meat of the talk, I know I know we've gotten into a lot of background from other speakers, and I kind of want to take us back on a little bit of a journey of where we've been in history, right? We've driven to this continuous, smaller, more compact system space, and it's been pretty phenomenal. I think we saw a graph earlier of going from gigabit type switch systems all the way up to 51 terabit, which is absolutely phenomenal growth. And we're doing a really great job of this, right? If it can fit in a reticle, it makes a lot of sense to drive smaller, right? You can get efficiencies, power, speed, all those benefits. And I think you've heard throughout all these talks that we can do a lot on a chip, right? We can bring a room-size compute system down into the palm of our hand, right? Into something smaller than our phone, right? We have a ton of chips in here. But if I tell you right now to put your phone in airplane mode, probably none of you will take it out and do that. Because one of the things that's absolutely powerful about this device is not the fact just that it has a strong compute system within it, but that it can connect to the millions, trillions of compute systems, storage systems that are out there in the world, right? Thanks to Facebook, Meta, we got Facebook, we have Instagram, we have Google, we have your email for your work. You're probably taking it out 1 million times a day just doing that. And that's what's important, right? It's the connections that we're making. And it doesn't matter where we are in the world either, right? We're making these connections count. We can be here, we can be in Bangkok, we can do the exact same the same things on our system if we can get linked up. Right? And that's pretty phenomenal. And yes, I'm talking about the internet, right? We like the internet, and it's great. But one of the things that's important to note is that internet's been driven by optics, right? Historically, it was electrical links, but now it's pretty much driven by optical links. And what we're seeing in a data center or an AI/ML system today is that while we have optics in the data center, and we've scaled in the same way that our internet scaled globally, the rack is still the limiting factor, right? That's what's being connected up by copper cable. And as we go to these higher speeds, we're getting limited by that copper cable, right? We're doing things like shorter link lengths or thicker cable to deal with it. That has impact on the amount of power we're using to drive that electrical link. And that also has impact on just things like cooling, right? How do you get all that air through that space? And anecdotally, I've also heard that just the weight on the floor has become an issue in infrastructure. So it's pretty significant. And in fact, that same challenge, right, is being driven inside the box, right? We have flyover cables now. We have a lot more connections. And if you try to scale that to the next generation, what does that mean for the cables that are now inside that box? They're going to get thicker. They're going to get shorter, right? It's the same trends. We know this trend is going to continue. And if you look at that kind of graphically, right, you can see as you go to these higher speeds, you're going to follow along the same trend. And at some point, that's going to break. And I think you're all here because you, at some point, believe that that is true. And if that breaks, then why are we designing a system that's optimized to have copper, right? Why go to the effort of having your protocols, your power, everything optimized for simply to have copper, have that option? And so at Broadcom, what we developed is a forward-looking concept that we're, in fact, deploying today. And this is our Silicon Photonics chiplet in package. The idea behind this is it's a semiconductor scalable process So we're stacking chips. We're doing the same thing as a previous speaker, NVIDIA, talked about high bandwidth memory and what's been done in that space, right? We're stacking chips in the semiconductor processes. We're also able to do SMT processes, right? Solder reflow in the same way that you do any other system or chip. And in doing this, one of the biggest components that we need to also do is have a detachable optical connector. No one really wants to have fibers dangling off the system and have those go through solder reflow and potentially break, and then your whole system is thrown out, right? That would be pretty catastrophic. So we put a detachable optical connector, and that allows us to do a lot of these things in scale. And what I'm showing on the right is a transceiver-based system where we integrate our SCiP package into DSP, right? So we're co-packaging with a DSP in this case in a traditional transceiver space. That allows us to let networks that are not quite ready for the jump of CPO to test out the technology. We can use that exact same platform and scale it from something like a 400 gig all the way up to 6.4 terabits in one package, and co-package that with our switch ASIC, our 51.2 terabit switch ASIC. What I'm showing in this picture is what we are actually demonstrating right now is 25.6 terabit, half optical, half electrical. That's downstairs in the Ragile booth. So if I delve a little bit deeper into what is this co-packaged optics, how do we do it? The core principle behind the solution is ensuring that we are staying pitch matched from that core silicon. And quite honestly, it could be whatever core silicon you want it to be, right? It doesn't have to be a switch. But we're staying pitch matched from there through to the optical engine. So that's, zoom in here of that capability. And of course, the photonics themselves, the photonic IC has to be incredibly dense. We've done some really great work internally to drive that footprint down. And then we have to integrate with the EIC, the electronic IC. And so we use, micro vias, we have micro BGAs, all of the things that have already been developed in the industry because of the need for getting connections out, right? We've heard this. NVIDIA talked about this with their HBM stacks. And then lastly, you need to get the light off. So what we've done here is in the footprint of a single MPO, we've put the equivalent of 5 MPOs. That's a detachable connector to our optical chip. And doing this allows you to get that escape density, right? So we've heard a lot of talks from the keynotes yesterday through the talks today about getting information off that chip. We can do a lot to scale the chip, but getting the information off is the challenge. And if you follow the blue curve on that plot, what you see is a growth of about 40x potential as you scale from front panel pluggables through to co-packaged optics, and then you start adding wavelengths, right? 4 wavelengths, 8 wavelengths. The beauty about fiber, I don't know if you guys know this, but you don't actually have to make it bigger to put more data on it. It's fantastic. And if we compare this from pluggables to optics, in co-packaged form factor, we can get at least a 50% savings. And one of the things that we have on this graph here is we're actually plotting the transceiver power, assuming that you're going to go to lower nodes, like 3 nanometer nodes in the future. But our CPO power is assuming a 7 nanometer node, what you can do today, right? You don't have to scale that to get this power savings. Now, if you want more power savings, yes, we could consider scaling that further, but you can get the cost, right? We've heard that a lot as well today. I think Microsoft casually mentioned that a few times. So, those benefits can come in. And of course, once you do that, there's a lot of different architectures, and we've heard about some of them. These are just a few where, you can start co-packaging this with other types of technology, like XPU, do resource pooling, memory disaggregation, what have you. So, I looked at, this is my first time here at SCiP, so thank you for having me. And I've been really impressed with the talks and what I've learned here. But I took a moment to look at the mission statement. And I said, okay, what are we doing? And how does this align with OCP's mission? And I always say CPO, OCP, it's all over the place. But scalable, efficient, and flexible, right, are huge areas of this space. And the platform approach, right, having this co-packaging, allowing you to scale from 400 gig all the way up to 6.4 terabits is huge. That allows you to integrate not just with transceivers, but also with NICs, right, of the future. It allows you to integrate all the way up to high-performance computing and anywhere in between. It's efficient. I've already spoken about the power savings of the system. And that's just, I would say, a tip of the iceberg, because we haven't really looked at the system-level savings that could also go through. But if we start looking at the system, we're looking at the thermal, the airflow, all those things, right? The fans don't have to run as hard, which means they're more efficient, right? Which means we save even more power. It's not a linear scaling here. And the other area is, 1RU. We saw a talk earlier, how do we get to 1RU? This is a way that you can get to 1RU. And it's flexible. As I mentioned, you can do solder reflow onto a board, and it's the same processes that your standard CM can do. And I just want to point out that this is real, right? So we announced earlier that we're doing this in partnership with Tencent and Ruiji. Ragile is their American arm of Ruiji. And we're showing this here today. I welcome you all to go down to the showroom floor and to Ragile's booth and take a look at our 25T system. I don't know how that got there. All right. So we're showing this. It's a half optical, half electrical solution, co-packaged optics, interoperating with a DR4 pluggable module. So you can see the whole ecosystem kind of in one little table there. Now, why am I here to talk to you, right? I think there's a lot of innovation in this space that we can continue down the path on. Once we have a product like SCiP and other competitors doing this in the ecosystem, we can then integrate that in many different ways. But this integration also allows us to alleviate that link length distance, right? We can now be, generally speaking, distance agnostic, once again, like the internet. And we can enable disaggregation, memory, resource pooling, XPU, what have you, right? Next generation architectures that we haven't even considered today. We can also look at novel physical designs, right? How do we actually look at modularity of a system now? We've spoken about the rack not being a rack, putting a TOR at the top, doing other things that you can do in that space. But I'm sure there's a lot more, even at the blocks level, that could be done in terms of modularity when you start moving to a system like this. So I welcome, I'm now allowing you to go get some snacks. Please come up and talk. I'd love to hear your ideas on how this could go further and really generate the next generation system. And you're also welcome to take a look at our URLs there for more information about our stuff. Thank you.